All right, I'm going to talk to you about particle physics. You're going to become a big-time expert on particles and how they make up matter. And this is always kind of a fun assignment for everybody. So to start this out, let me put on a table here. And in this table, I'm going to list out the different kinds of particles that there are. All right, so to start off with, let's put in quarks. Now these particles are fundamental. As far as we know, we can make them no smaller than what they are. So, we don't have anything else that they're made out of. So there are 6 different kinds of quarks. There's the up quark, down quark, the charm quark, the strange quark, the top quark, and the bottom quark. Now these are very strange names to give something, but for lack of better terms, and they have something to do with their spins and things like that, so it's not just totally random how they assign these. You just have to get used to these kind of different names. Okay, so these are quarks. There are also things called leptons, and let me change this here. All right, so leptons. Now these are much smaller than the quarks and things. These are really, really tiny. They include things like electrons, things called M particles, and tau particles. You may have heard neutrinos. There's actually 3 kinds of neutrinos, and they're represented with this strange looking V. The electron neutrino, the M neutrino. Guess what goes here? I'll bet you can't guess. The tau neutrino. Okay, so these are all the different kinds of particles. These are all particles. Okay, and we also have something called gauge bosons. And these aren't technically particles, they're exchange particles. They are things that are thrown back and forth between the other particles to represent things like forces. And we have different ones. Let me make a color change here. And we have different ones. We have one that you're all familiar with. That's the photon. We have the gluon, the W particle, and there's actually a plus and a minus W particle. And then we have the Z particle. Now these particles are associated with the 4 forces. So we know that there's electromagnetic force. So that's what the photon is associated with. The gluon is part of the strong force, and W plus and minus and the Z are part of the weak force. Weak nuclear force, strong nuclear force, electromagnetic spectrum. Well, what am I missing? It's pretty obvious that I don't have gravity represented on here. That's because we haven't found it yet. We haven't found what would be called the graviton. So that would be another particle that we would need to find to complete this whole set. Okay, so there is everything that we need to know. All of this stuff has been found in the different collisions that they've had in the particle accelerators. And usually they take protons and they smash them together at almost the speed of light, not quite, but they put a lot of momentum into those little particles, smash them together, and they see what comes out. And there's a pretty good picture in the book about what they experience when they come out. They put it in electric field, and then based on which way these things swirl in the electric field, they can tell what the charge is, and if they don't swirl at all, they can tell there's no charge at all. So that's how we know what these different particles are. We've seen them from all of the different collisions. Okay, there are different things that you need to know about, and we'll get to where these are. Now this is a very simplified version of the chart that's in your book on page 290. You'll want to know that. It's a good thing this chart is also in your data booklet, so you don't need to memorize it, but you need to be very familiar with it. And you'll have a lot of fun with this kind of stuff once you understand that table and how everything works. So I'm going to give you a great big overview of that now. Definitely read Topic 7.3, because that will give you a lot of familiarity with this, along on top of this video. So we also have some numbers, like the periodic table has atomic mass and the number of protons and atomic number and things like that. Well, we have some numbers we need to associate with this stuff too. There's charge, there's baryon number. Let me go ahead and spell that out for you. Baryon number, lepton number, and strangeness. Now, these are all important numbers when you are experiencing nuclear reactions, nuclear decay, and things like that. Just like with every chemical reaction that you've ever done, both sides of the equation have to equal. All of these numbers have to equal the other side. They have to be equal on both sides. And we'll get to what that means here in just a little bit. But let me give you what these different numbers are. Okay, so I'm going to create right down here a little box. Okay, it represents what's inside each of these boxes. So I'm going to put the strangeness number for each one of these here. I'm going to put the charge here, and I'm going to put the baryon number here. And this is only for quarks, okay? Only for quarks. So leptons have a different thing. So this is for quarks only. Okay, so each one of these quarks, these 6 quarks here, have a charge. The ones on the top have a minus 2/3 charge. Minus 2/3 and minus 2/3. I take that back, they're plus. They're positive 2/3, all of them. All right, positive 2/3, positive 2/3, positive 2/3. And on the bottom, they're all minus 1/3 charge. This is 1/3 of an electron's charge. So you'll also see it represented as E. All right, let me actually come in here. I want to get rid of that. Let me come back here and do this again, and let me try to lighten up that color so it's a little easier to see. All right, so it's plus 2/3, plus 2/3, and plus 2/3. This is minus 1/3, minus 1/3, and minus 1/3. And again, let me draw the box here so that we remember what we're looking at. This is the charge. Strangeness will be here, and baryon number will be in this corner here. Okay, so every one of these has a baryon number of 1/3. And I'll explain what we mean by baryon here in just a minute. And they all have a strangeness of 0, except for the strange quark, which has -1, which seems weird. So one thing I want to cover with you is these are all normal particles. These are the particles that we usually deal with. But there is such a thing called antiparticles. Okay, and so antiparticles are exactly the same. They have exactly the same characteristics as our normal particles, except they are oppositely charged. So they are exactly the same except for the charge. So electrons are negatively charged, so a positron is an anti-electron. We could call it an anti-electron, and maybe we should, but the convention is to call it a positron. However, if I have an anti-up quark, put a line over it, whereas this charge is +2/3, this charge is -2/3. But it still has a baryon number of 1/3 and a strangeness of 0. You know, a strange quark has a charge of 1/3 and a baryon number of 1/3. That doesn't change, just the charge, and a strangeness of, let's see, put a line over here, strangeness of +1. So the only thing that changes is the charge, but on the strange quark, the strangeness becomes a +1. All right, so just think about that for a little bit. This is all covered in the chart in your book and in your data table. So, you know, be aware of that. Okay, so what kind of particles are? How do they all relate to each other? All right, we all matter. All matter is considered fermions. Okay, fermions. That's just matter. That's all the particles, not the force particles. These are exchange particles. We're only talking about these particles over here. So fermions, there are two kinds of fermions. There are hadrons and there are leptons. Okay, hadrons are all of these. They're basically all of these particles that are not leptons. All right, so leptons are the electrons, the M's, the taus, the neutrinos, all of those, and they're the anti ones as well. Okay, so you can have an anti-lepton and a lepton. You can have a hadron and a non-hadron. Hadrons are particles made out of quarks. So there's two kinds of particles made out of quarks. There's the baryons, which I mentioned before, and then the mesons. Okay, baryons are made out of 3 quarks. Mesons are made out of 2 quarks. One of them is a normal quark and one is an anti-quark. Okay, so baryons don't have that. They can be any kind of quark, but it has to be 3 of them. Mesons, and I don't believe you need to really know this, but you know, we'll just for completeness. There's 3 kinds of mesons: the pi meson, the K meson, and the N meson. And each one of these is made out of one of the normal quarks and made out of an antiquark. All right, so baryons. The two most famous baryons that we know about are protons and neutrons. Each one of these is made out of 3 quarks. And so basically, the only ones you're really going to have to worry about are the up, down, and strange quark. Mostly the up and down. But let's look at what these are made out of. All right, so protons, let me write it over here. Protons are made from 2 up quarks and a down quark. So let's look at this. Let's look at how these quarks affect the charge, the baryon number, the lepton number, and the strangeness. So you could also write this up, up, down for the different quarks that there are. Okay, so charge. So up quarks are positive 2/3 charge, and a down quark is negative 1/3. If you add that up, 2/3 plus 2/3 is 4/3 minus 1/3 is 3/3, so it's a positive 1. The baryon number is 1/3 plus 1/3 plus 1/3, and again that equals 1. So it's got protons have a charge of +1, which makes sense because they do. A baryon number of 1, a lepton number. Lepton number is what these are. Leptons, they all have a lepton number of 1, unless they're anti-leptons, then it's -1. But these are not leptons, so they don't have any lepton numbers, so it's 0. And strangeness, all the strangeness numbers are 0, 0, 0, 0, unless it's got a strange quark in it. So since it's all zeros, it's 0. So proton has a set of numbers, a charge of +1 and a baryon number of +1, a lepton number of 0 and a strangeness of 0. Neutrons are made of 1 up quark and 2 down quarks, or up, down, down. And the order doesn't really matter how you say those. You could say DUD, but then the neutron would be a dud, and that would be no good. Yeah, sorry about that. Okay, so and let me give myself a little bit more room here than I did before. Strangeness. Okay, so the up is plus 2/3 minus 1/3 minus 1/3, and so that charge equals 0, and it should. It's neutral, no charge. A baryon number 1/3 plus 1/3 plus 1/3 equals 1, and that's good. That's it's a baryon, so all baryons should be 1. All antibaryons should be -1. Lepton number again 0, 0, 0, so it's 0, and there are no strange quarks, so it's 0. So those numbers all have to be in agreement on both sides of, say, a nuclear decay equation. Okay, so let me give you an example of that. Get rid of all that. Okay, so nuclear decay equation. A neutron decays into a proton by emitting an electron and an electron anti-neutrino. Now, mainly, I don't know if this is actually true. I've seen this equation, but I need to figure out if it is true, if everything on this side adds up to everything on that side, if the charge adds up, if the baryon number adds up, if the lepton number adds up, and if the strangeness adds up. Okay, so this is made with an up quark and a down down. This is a down, I'm sorry, this is an up up down. So I get 2/3 minus 1/3 minus 1/3, so my charge is 0. Here my charge is 1, but because this is an electron, the charge is minus 1, and there is no charge on these neutrinos. The only charge, let's see, charge here is -1, -1, -1, 0, 0, 0. Would be 0, so is 0. So those two sides match. That's good. Baryon number is 1/3 plus 1/3 plus 1/3, because all the baryon are 1/3. So this is 1. And this is 1 for the proton. We just did that on the other side. Leptons have no baryon number, just like baryons have no lepton number. So that's 0. Another lepton, 0. So the baryon number is 1. Over here, no lepton number. We have a lepton number here of 0. We have one of +1, and since this is an antineutrino, it's a -1. And so the overall lepton number is 0, just like over here. And a strangeness, no strange quarks in there. No strange quark, no strange quark, no strange quark equals 0. All right, so 0 equals 0, 1 equals 1, 0 equals 0, 0 equals 0. This is a valid nuclear equation. Okay, so this is how you will actually see on a test. They will give you these, and that's all they'll give you, and they'll ask you to verify if this is a possibly correct equation, if this is feasible, or if it's realistic. Could ask you that in any of those ways. All right, so let's look at just one more to finish this out. So protons will decay, and they'll give you other things, but they will always tell you what the pieces are, unless they have you solve this using the notation to figure out what the particles are, and then we'll ask you if this is feasible, and then you go into this process. Okay, so proton becomes a neutron by emitting a positron, an anti-electron, plus an anti-electron neutrino. All right, so charge, and set it up this way all the time. This just makes it so much easier to track. Lepton number and strange. We already know there's no strangeness here, so no strangers. Lepton number, 0 here, 0 here. There is a -1 here, and this is an anti-neutrino too, so it's -1 equal. Well, there's a problem. This is not feasible because we have -2 on this side and 0 on that side. What would make this is if this was not an anti-electron, but if it was a normal electron neutrino, that would be plus, and that would make this 0, and then it would match. Baryon number is 1, 1, 0, 0, so it equals 1. And charge is +1, neutral, +1, 0, so it's +1. So the actual equation of this is a proton decays into a neutron by giving off a positron and an electron neutrino. All right, so that is a very quick and thorough introduction to particle physics, and you should have a really fun time playing with these. and understanding. Make sure you read the entire unit, the entire topic 7.3 to get a complete and thorough understanding of this. We'll see you in class.